All right, in this video, we're going to take a look at how buffers work, and we're going to compare how a buffer works to what happens with pure water. So what I have here is I have a sample of pure water in the beaker. The pH is reading to be about 7.4-ish here. And what I'm going to do is I'm going to take a beaker. This has got some like 0.1 molar sodium hydroxide, and I'm just going to add a squirt of sodium hydroxide to my water there. And notice how, even though this base was not very concentrated, the pH changed by a lot. It went from 7 to 10. Let's try adding another squirt and see what happens too. Okay, so we had 2 squirts there. So we had a pretty big change in pH. All right, so that's pure water. Now let's try it the other way. So this was adding base. So now let's do it where we're starting with, where we're gonna add acid. Oops, my pH started a little high. I got a little cross-contamination. That's okay. All right, so now I'm going to add some acid to my water. Let's add 2 squirts of acid, just like we did 2 squirts of base earlier. Notice that when I add the acid, the pH also drops dramatically. So when we add a little bit of acid or a little bit of base to water, our pH is changing by, a full, at least like maybe 4, like 5 pH units. So we're getting a pretty big change in pH. So now, by contrast, what we're going to do is we're going to make a buffer. So a buffer is made with a weak acid and its conjugate base. So this right here is acetic acid. Okay. And then we're going to add some sodium acetate to it. This contains the conjugate base of this weak acid. So I've measured out 5 grams of the sodium acetate right here, and I'm going to add it to my weak acid, and that is going to give me a buffer, and I'm going to stir this up to mix them. And buffers, the pH of a buffer is going to depend on the strength of the acid. So it's going to depend on the pKa. So to find the buffer of this, to find the pH of this buffer, I'm going to look at the pKa of acetic acid. And the pKa of acetic acid, if you go and check your OneNote page here, the pKa is around 4.7. So when I stick my pH meter in this mixture, I expect it to be around like maybe 4.7, 4.8, somewhere in there. All right. There we go. I'm going to now take my pH meter. I'm doing bad technique. I should rinse it, but I'm not for the sake of time. Okay, now I'm putting it over here in my buffer mixture. So my pH here is around 5.6. So if I have exactly equal amounts of my weak acid and conjugate base, my pH should be right at my pKa, but I didn't necessarily add equal amounts here. Okay. So here is my buffer. Now I'm going to take this buffer and I'm going to split it in 2. I'm going to pour a little bit in this beaker and keep a little bit in this beaker over here. And then I'm going to see how well my buffer works. I'm going to go back and do the same thing I did with the water, right? And remember with the water, when I added 2 squirts of base, the pH changed by like, 4 units, right? It changed a lot. Look at this. When I add 2 squirts of base here, the pH, I don't think it really changed at all, right? So it's still like 5.6. So really dramatic difference what happens here with our buffer versus what happened with our pure water, right? Okay, now let's do this one, and let's add some acid to this half. We're going to put in some squirts of acid, swirl that around. Again, the pH does not change at all. So this is a good buffer. Maybe it changed by like 0.01 or 0.02. So that's what we mean by saying buffers resist changing in pH. So when you add some acid or base, the pH does not change very much. I mean, see how different that is to a non-buffer like water. The pH changed dramatically. You could also, when you think about buffers, you can think about the buffer capacity, which basically is like how much acid or base can you add before the pH starts to change. So you could like try putting in more acid and see how even if I just add like 20 mils of acid and the pH is still pretty much staying the same. At some point, if I added enough acid, then my buffering components would all get used up. Because what's happening right now is I add acid to this buffer, the weak base in the buffer is neutralizing any acid that I add. At some point, if I add enough acid, all of my weak base will get used up and my buffer will basically be broken and won't work as a buffer anymore. And that's what we refer to as like the buffer, what we think of as the buffer capacity. It's like how much acid can you add to it and have it still maintain a steady pH. So this buffer is got a relatively high capacity. I added like my whole sample of acid and the pH is still keeping relatively constant here. The way that you increase your buffer capacity is just to increase the concentration of these components. So this buffer we actually made using like 0.5 molar acetic acid and 0.5 molar sodium acetate. If you'd made a buffer that was just like 0.1 molar, it would have a much lower buffer capacity. If you made a solution that was like 2 molar, it would have a higher buffer capacity. But in all those cases, this buffer's pH would still be about pretty similar to the pKa as long as your ratio of acid to base is staying the same. All right, I was just throwing in a few other miscellaneous topics here into the video, but here's some buffers in action. Successful buffer experiment here. All right,